Welcome to this Algebra 2 session on sets of numbers. So what we're going to do today is distinguish between types of numbers, describe sets using a verbal description, roster notation, and set builder notation, determine intersections and unions of sets of numbers. So what I'd like you to do is try this matching on your own first. You can pause in the lower left-hand corner and then turn it back on once you finish to see if you got the correct answers. But I would like you to try it to see what you know about these. So if we look at the first ones, we're matching 0, 1, 2, and 3. We want to know if that's integers, a group of integers, natural numbers, whole numbers, or real numbers. So it is a group of whole numbers, so it's C. Whole numbers start with 0 and increase. So basically it looks like the integers, but it's the positive integers including 0. Then if you start your set with 1, 2, 3, that would be the natural numbers, so that would be B. And then for number 3, -3, -2, 0, 2, those would be integers because you have positives and negatives in this group, and you have 0. And then -100, 3/4, 10.2, 22, those are all considered real numbers. So basically all of these are considered real numbers. Now that's just kind of a little bit of a review of the numbers that we work with. There's more in your lesson, there's more in your reference guide. So if you had trouble with these, please look over that part of the lesson because they are going to ask you some questions on the quiz about that. If you need to pause, you can do so. We're going to move on here. Rational versus irrational. So let's cover up our definitions here first. Nice bright red. What's the difference between rational and irrational? Well, rational numbers can be expressed as a ratio of A over B. So that can be your integers because if you think about the number -5, that's a rational number because I can write it as -5 over 1. Your terminating and repeating decimals are considered to be rational numbers. So that means fractions such as 3/4 is a rational number because 3/4 can be written as, of course, A over B as a fraction, but it's also a terminating decimal. So that's what we mean by terminating decimal because 3/4, let's write this up here, 3/4 is equal to 0.75. So it's considered a terminating decimal. It's written as a fraction, so it's considered a rational number. Repeating decimals would be something like 1/3 because 1/3 is 0.3333, and it goes on and on and on with a repeating pattern. Irrational numbers, on the other hand, are non-repeating and non-terminating decimals. So a very common irrational number is pi, 3.14, and it goes on and on and on. So it doesn't terminate and it doesn't have a repeating pattern. So pi is probably the most famous irrational number that we work with or most used. Some others, you can check on your calculator, the square root of 2. It only can show so many places on your calculator, so you'll see that it does come to an end, but that's only an end at the end of your calculator. It does go on and on and on, and there's no repeating pattern. So you're going to see some symbols throughout this lesson and probably throughout our units in Algebra 2 that represent symbols that represent the different categories of numbers that we work with in our system of numbers. So rational numbers are symbolized with a Q. So that indicates the set of rational numbers. Natural numbers, N, are integers. Now you would think I, however, the symbol for integers is Z. Whole numbers are W. Real numbers are R, and it's usually a fancy looking R, and I get a lot of questions. What's that fancy looking R? It represents real numbers, okay? Irrational is where the I is. So you can see for rational, we can't use R for both rational and real, so that's why rational has to be Q. And integers are z rather than an I because we use I for irrational. So you can pause if you need to. We are going to move forward here. Sets. A collection of objects is called a set. The members of any set are called elements. Elements can be numbers, objects, people, or anything. So if we're talking about the days, the months in a year, that would be, months of the year would be considered the set. The elements would be January, February, March, April, May, and so on. So sets can have numbers, but they can also be talking about people or objects or anything like that. So what's the difference between these examples here? Well, you can see we have 2, 4, 6, and 8. Cat, dog, mouse, -100, 0, 3, and 4.5. So compare those to these examples here. Well, what you'll notice is that we have ... which means on and on and on, ... That means that we are going on to infinity. So that can help you remember the name. These are called, on the right side, are called infinite sets. That means that they're going on to infinity. You may not always see the ... They may be written with words, such as the set of even numbers. That would be an infinite set because it goes on and on and on to infinity. But if you said the even set of numbers up to 20, that wouldn't be an infinite set anymore because we've put an ending point. 20 is our ending point. So for example over here, these all have an ending point. So they're considered finite sets. So if you have an ending spot, an ending number or object, then it's a finite set. But if not, it's called an infinite. All right, sorry I didn't ask if you need to pause. You can do that. You can always go back because it's like a recorder. You can fast forward, rewind, pause. All right, so let's talk about describing sets. There are 3 ways to describe sets that you're going to see here. One is roster notation. That's kind of what we've been looking at on the previous slides. S is equal to the set 0, 2, 4, 6, and 8. That's roster notation where you use the braces. And you just list out the elements in your set. Verbal notation would be to write it out in words. S is the set of even numbers from 0 through 8. Set builder notation is X. Now this may be a little bit more confusing, but they're all talking about the same set, 0, 2, 4, 6, and 8, all of these descriptions. So the way that we write 0, 2, 4, 6, and 8 in set builder notation, and actually we could have S equals here, we put X such that, this means such that bar means such that, X such that X is an even number. So we're saying that X represents each of the even numbers in the set. Actually, we could say X is an even number up to 8 if we want to be talking about that set there. Let's do that. X is an even number up to 8. So that would be set builder notation. You have a variable and you have a descriptive phrase about the set. All right, moving on. You can pause if you need to. Let's look at some more things about sets. So A is equal to the set 1, 2, 3. B is equal to the set 1, 2, 4, 5, and 6. Now, you might be wondering, what are these symbols here? The U, the upside down U, the sideways U. What's going on with these symbols? So the U means, we'll put it up here, union. And upside down U means intersection. And we'll talk about the bottom one when we get to it. So union means that you take the two sets and put them together. So you're going to combine your two sets. So my new set of A union B is going to have all the elements in both sets. So 1, 2, 3, 4, 5, and 6. Notice I don't write the repeats twice. I have a 1 in both sets, but I'm only going to write it 1 in my new union. So you're going to take each number in each set and make sure that it's in the union when you're doing a union. You're combining both sets together. Now an intersection is actually looking at where do they intersect each other. So you want to be looking at what do they have in common. That's going to be your new set. So intersection only contains the common element. So if we look at the two sets here, we have a 1 in both. So 1's going to be part of it. We have a 2 in both. So 2 is going to be part of our set. But that's all we have. 3, 4, 5, and 6, they aren't common in both sets. So 1 and 2 are the only ones that we have there for A intersect B. And then we have A with this sideways view, and that indicates proper subset. So the way we read that is A a proper subset of B? And the answer here is no, and I'm going to explain why. So proper subset means that it would have to mean that every element in A is also found in B. So when you say, is A a proper subset of B, is every element in A also found in B? And that's not true in this case. So what you're asking, is every element of A also in B? So that's the way you want to look at that symbol when you see it. So if it were the B first, is B a proper subset of A? The answer would be no there also, because 4, 5, and 6 are not found in A. So the answer is no if you do it one way or the other. Now the last thing we're going to do, so you can pause if you need to, is we're going to look at what's called a Venn diagram. And I'm going to put some numbers in here. And I was going to do that before I actually got to this slide, but that didn't happen, so we're going to fill it in now. So when you see an example or a problem like this that you have to do, the numbers are already going to be listed here. You're not going to be writing them in. So you would be looking at this, the numbers would already be there. So it's asking us first to list the elements of A, B, and C. So the elements of A would be to look at the circle A and write down all of the numbers that are in circle A. One, 3, 5, 8, and 9. So all of those elements are in the circle A. Then all of the elements in circle B are 2, 4, 6, and 8. Okay, so that's looking at circle B here. And then the elements for C, C is only this section here where circles A and B overlap. So C is going to have the element 8. Now we're asked to do some things with these sets. A union B and A intersect C. So A union B means, once again, that we're just going to combine the two sets together and create a new larger set. So the new set's going to have everything from both sets. So 1, 2, 3, 4, 5, 6, 8, and 9. So a union is going to be a larger set because you're putting everything together. A intersects C. So now we're looking at, where do A and C intersect each other? Well, we already talked about that a little bit. From looking at just the diagram, you can see that they intersect right here, A and C. So 8 is our intersection. You can also look at it from looking at the sets of numbers. A and C have only the 8 in common. So A intersects C is going to have only the element 8. All right, so that ends this session on sets of numbers. Be sure to do the reference guide questions and check your answers. Have a great day.